So finishing up our introductory section on mesh currents, we're going to do a couple more examples just to make sure we're comfortable with this approach, which remember is an alternative to node voltage analysis to find currents and voltages in more complicated circuits that don't have resistances that are in series and parallel. So in example 14, we're at the top, example 12, we're at the top of page 60 in the ECE 301 workbook. We have certainly a more complicated circuit in this case, and our goal is to write 4 independent voltage equations using mesh currents and assemble the 4x4 linear system. It's not necessary to solve for it. We just want to make sure that we can set it up so that if we had a matrix solver, had that software, we could plug in the rows for the matrix equation and it would solve for the unknowns, which would be currents in this case. So the best thing to do is to consider a sequence of KVLs. So we're writing independent voltage equations, so we're going to be using KVL. And as you can see in the diagram, you have 4 mesh currents, okay, all in this planar network here, and they're all are going clockwise. So what we do in this case is we'll start off any one of them, we'll do them in order. So we'll do KVL on mesh 1, which means we're referring to this upward loop here. We're using this mesh current 1. And the idea, remember, is to assume as we go in this direction of this mesh current, we're doing PRC across all of our resistances, and we're just going to subtract off components of current that are coming from other meshes, okay? So that we're always going to be in mesh 1 doing I1 minus some other mesh current, for example, if it's sharing that resistance. In this case, we can see the second mesh and the fourth mesh are sharing resistances in common, all right? So with this first one. So let's go ahead and look at KVL. We're going clockwise around, and let's start up here. So in this case, this resistance is not being shared by any other part of the mesh. So this is simply going to, its voltage is simply going to be R1 times V1, R1 times I1, that mesh current, and that gives us the voltage there. Then we would come into R2. And again, this is what I meant earlier. In this case, this resistance is shared between these 2 meshes. We'll assume we're going in the direction of PRC for I1. So then we will subtract off I4, okay? That will be the sum of the currents coming through R2, assuming we're coming the direction from the top down. So we use positive I1, and this mesh current would be reversed order. So it'll be adding a negative I4, okay? Continue on around the mesh here. We come into R4, and again, it'll be I1 minus this opposing mesh current there, right? And then finally, we come into the negative polarity of that voltage source, and there's your first equation, okay? And again, we will set up the matrix equation in a minute according to the unknown vector I1, I2, I3, I4. But for now, this is good enough. We have what we need. So we'll continue on and do another KVL for mesh 2. Again, these are all KVLs. So mesh 2, we're in this triangular structure here. And we'll just start, again, it doesn't matter where we start. We'll just say, suppose we're starting and coming through the R5 resistance, which is not shared by any of the other meshes. So in this case, the voltage will be just R5 times that mesh current I2 plus, and coming up to R4. We've seen this before. So in this case now, the current, the sum of the currents through that will be I2 minus I1, right? Because you could also look at it as this current is opposing this one if we're doing PRC in this direction, okay? And then finally, we need to come through R6, and you should see what's going to happen here. You will have I2 and then minus I3. You're always subtracting off another mesh current opposing the direction you're flowing, okay, through that resistance. And there's no other there is no independent voltage source here, so this just equals 0, okay? Continue on, let's go to mesh 3. And in mesh 3, we are down here, another triangle here. We'll start off by, let's flow through R7, and there's no sharing of that resistance with any of the other meshes. So that voltage will be R7 times I3. Then we will come up into R6, again, being opposed by I2. So we'll have plus R6, I3 minus I2, and then it comes over to 8. And for 8, we would have I3 minus I4. Right? And that will be equal to 0. Okay. And one more mesh to go. Right. So mesh 4 over here. 3 resistances to work with. R3 is isolated, so the current coming through R3 is only I4, so it'll be, the voltage would be R3 times I4 for Ohm's law. And then we'll come into, let's say, R8, which is shared with 3 again, so we'll have plus R8, and then in this case, it'll be I4 minus I3, and then we will come up through R2, right? And that'll be our I4 minus I1, okay? And that has to be equal to 0, right? So having done that, all 4 KVLs, it's not necessary to see all the circuit now, so we're going to go ahead and produce the matrix equation. So let's see what this matrix equation looks like. Allowing our room here. In this case, it's larger because we will have 4 rows. And you have 4 mesh currents and a right-hand side vector, okay? Right? So all we have to do, remember, is read off all of the components of the coefficients of each one of these as we go across a row. So for the very first equation, okay, we're looking for I1s. We have R1 times I1 there, R4 there, and we also have R2. So the very first component up here will be R1 plus R2 plus R4. The second component would be, do we see any coefficients for I2? Yes, we do. We have a negative R4. Do we have any I3s here? No, we don't. So there'll be a 0 there in that position. And then we ask, are there any I4s in here? Yes, there's 1, and the coefficient would be minus R2. And again, this constant would be pulled over to the other side. So there's your first row of your matrix equation. Let's do the same thing now. Go ahead and continue on. Again, starting with this second mesh equation here. What are the coefficients for I1? We would have negative R4. What about I2? I see an R4 and I see an R6 and I also see an R5. So this is kind of large. So you have 4, 5, and 6. What about I3? Oh yes, there is a coefficient for R6. In this case, it's just minus R6. There we go. And finally, for I4, we have nothing. So 0 there. And there's no other term to pull over to the right-hand side, so you have a 0. Okay. Coming down, mesh 3, third row. Any coefficients for I0? Excuse me, for I1? No. So this will be a 0 term there. What about I2? Oh, there's 1. It's minus R6. And what about I3? 3 of them. 6, 7, and 8. So you have R6 plus R7 plus R8 in that position. And then what about I4? You have only 1, negative R8. Okay. And then last but not least, here we go, there at the bottom. What about I1 coefficients? You're going to have 1 of them from this multiplication, right? You get minus R2. What about I2? Scanning through here, see nothing, so this is 0. And what about I3? Well, I see a minus R8. And then finally, I4 will have an R3, an R8, and an R2. So we might put those in order, R2 plus R3 plus R8 in that position, okay? Again, that was kind of hard to see, that's an R8, okay? Now, if you step back for this and just look for a second, something very interesting just happened. Oh, and of course, these right-hand sides are 0. Sorry. Notice a nice property of this 4x4 matrix. It's definitely a 4x4 linear system. It's of the form, let's say, AX equals B. This is the B vector, this is the X vector, and this right here, we'll just say is the matrix A there. So again, we are solving a 4x4 AX equals B linear system. Interesting thing is this matrix is symmetric. Notice that the first row is equivalent to the first column. The second row is equivalent to the second column. That's very typical when you use mesh currents like this and a planar network. You're going to get this wonderful property. In terms of a complex network, it means you really would have to solve it. You could use special algorithms. One, for example, is called Kcl algorithm, where you could exploit just half of the data entries. You don't need to store the whole matrix. You can store half of it. The lower triangular or the upper triangular part. It's kind of cool. Another interesting thing is if you look very carefully at these, if you look at the matrix in terms of how it represents the network, it's very interesting. The first row, this diagonal element was resistances 1, 2, and 4, right? Notice the resistances that are in mesh 1, 1, 2, and 4. Notice on this diagonal, the resistances in this position, the 2, 2 position were 4, 5, and 6. That's not surprising. That's exactly the resistances in mesh 2. So in other words, the diagonal element is just indicating the sum of the resistances that are involved in that particular mesh, right? What about the off diagonal elements? Well, the first mesh is adjacent, in other words, is sharing R4. Notice this entry is minus R4. And also it's sharing R2. Notice the minus 2. So it's kind of cool, isn't it? What that means is it's very possible in this case to write code that takes and analyzes this network and goes straight to this matrix equation without having to do this, right? Because the adjacency of the meshes and which resistances are shared determine who's on the diagonal, and you'll end up changing it to the negative sign there, and then who goes on the diagonal, okay? It's really, really nice, all right, that you can see the connection between the elements of the coefficient matrix and the topology or the layout of the circuit, okay? So let's, getting one more practice, we're gonna go on to page 61 and do an example and then check our result with mesh currents using our previous methods, just to show you that you can go either direction, node vocal analysis, or you can go with mesh currents. So for this problem in 13, again, we're at the top of page 61, you have two meshes here, again, closed planar paths here within the network, and you have one independent voltage source here of 100 volts, right? So let's just start off and do your KVL for mesh 1, and then you'll do a KVL for mesh 2, and see if we can then use that and maybe other information to figure out how to solve for the current flowing through the 10 ohm resistance. So this is the target, the current through that 10 ohm resistance, right? Okay. So using KVL mesh 1, all right, coming into the negative pole there, we'll have negative 100 volts, so we'll put negative 100. Then that current I1 will flow through the 5 ohm resistance, so we would have plus 5 times I1. And then we would come down through the 10 ohm resistance, assuming, again, this direction here, it would be opposed by I2, so we'd have plus 10 times I1 minus I2, and that would have to be equal to 0. Okay, we could clean that equation up a little bit, but before we do that, we'll just leave it like this is for now. But you know, I don't know. Let's think about putting 100 to the other side, and you have 10 I1 and 5 I1. So I guess we could say this is just simplified as what, 15 I1 minus 10 I2, and then pull that 100 to the other side. So that's just it's a little bit nicer to work with. Okay, Very simple equation relating the two mesh currents. Come over here now, right? In this case, there is no voltage source. So we're just going to go around here with our mesh current. And notice that right off the bat, if we come through this 10 ohm resistance, we will be opposed by this other mesh current. So the sum of those currents will be I2 times minus I1, I2 minus I1. Then we'll come through the 5 ohm resistance only with I2, right? And then we would come through the 3 ohm resistance only through I2. And that would have to be equal to 0, okay? So cleaning this up a little bit, in terms of coefficients, we would have what? Minus 10 I1, and then you will have a total of what? 7, 3 is 10 plus 10 plus 20, I2 has to be equal to 0, okay? So we have a linear system here that we can solve. We could write the matrix equation for that. We could do that here over here, but we can also solve it by hand easily. But what we have shown is we would have this matrix equation, 15 minus 10 minus 10, 20. It's symmetric. I1, I2 equals 100 and 0, okay? Right. But we'll just do this by hand. So what we can do is notice, take the second equation. And so from the second equation, I mean, it's just an alternative to using Gauss elimination. We can do it by substitution. From the second equation, what we know is that I1 really has to be what? 2 times I2. Has to be twice whatever I2 is, right? Because that's the only way. If you have, if you take the negative 10 I1 to the other side, you could divide through by 10 and you would get this result. So that's very helpful, because now we can take this and substitute this result. Substitute, a couple of ways we could do it. We could substitute 2I2 for I1 in the KVL mesh 1 equation. And let's just do that, okay? So if we do that, what we'll have is 15 times what we just said. 2I2 is another name now for I1, okay? And then we'll subtract 10I2 and set that equal to 100. And clearly that's going to give us 30I2 minus 10I2. That's going to give you 20I2 equals 100, which says that I2 is really 5 amps, okay? Right? Right? So therefore, I1 must be what? Well, if I2 is 5A, we know it's twice whatever I2 is, which is twice times 5 amps, must be 10 amps, okay? Right? So, but that wasn't the question. The answer was, so the current through the 10 ohm resistance and we will mention, let's take the reference direction downward. So that's, you do have a choice of how you want to define the reference. So we're going to say the current reference for it is this direction, okay? And you'll see the significance of doing that. So we specified it will be going down. Well, then if it's downward like that, right? That means this would then have to be I1 minus I2, which will be 5 amps, okay? Now, if you said that for example, if the current direction was, let's just say if the current reference for the 10 ohms resistance was upward, okay, then what would it be? Well, then you would be using I2, right? It matches that direction, opposed by the other one, minus I1, okay? In that case, it would have been a minus 5 amps. But that was a different referencing. So it just depends on what the current reference is. So if someone's saying compute the current flowing through a particular resistance, you have to pick a reference direction, okay? Either either the problem tells you what it is, or you'll just say, well, if we assume downward it's this, if we assume it's upwards that, it just flips the sign, okay? Let's see if we got the right answer based on other methods. So we're just going to use other methods to compare it, and let's just do what we did earlier with maybe trying to reduce this problem, because one thing that you may have noticed that there's actually some series and parallelism going here. So we actually did mesh currents on a simpler problem, so to speak, but let's just see if we get the same answer. So we can get an equivalent here, right? So we'll get our first equivalent, because you could see immediately from the diagram, the first equivalent you could go for is series. So the first equivalent would be 7 ohms plus 3 ohms, and that would give you 10 ohms, okay? In other words, because those two resistances are in series. And so at that point, we would have, again, sketching it out, just making sure that we are consistent. You have a 5 ohm resistance still going through there. You still have a 10 ohm resistance, but now you have an equivalent, R1, and it's also equal to 10 ohms, okay? And very quickly, using, again, our approach of reduction, we can see these two resistances are in parallel. So we would have another equivalent, let's call it REQ2. And in this case, those two are in parallel, they're the same ohmage, so it's 10 times 10 over 10 plus 10, and that would give us clearly 5 ohms. Okay. All right. And the reason, again, is that REQ1 and the 5 and the 10 ohm resistance, right, are in parallel. Okay. So what we would have at this point is still have the independent voltage source coming through a 5 ohm resistance, now through another equivalent called REQ2, which is 5 ohms. So, and I think you see where we're headed. Our final equivalent is a series, right? So finally, you would have REQ is 5 ohms plus 5 ohms equals 10 ohms, okay? Again, because you have the 5 ohm resistance and REQ2 in series, it's just helpful as you're doing the work to verify and validate why you did that in terms of what properties you're exploiting. So then finally, we've produced this final equivalent of just a single 100-volt source with an equivalent of 10 ohms. REQ is 10 ohms, okay? Right? So in this case, what we've been able to deduce is we have the same current here. So this, again, is reduction using the same I1 mesh current there, right? So in that case, what we know then is that by Ohm's law, right, we should have, we have 10 volts, 100 volts there. And so therefore, and you have a 10 ohm resistance there. So we must have that I1 is 100 divided by 10 volts divided by, let me push this up, divided by 10 ohms would give you 10 amps, okay? So we have 10 amps, right, for I1, okay? All right. So now if we want I2, right, we're going to have to push back up again to this case because this resistance was being shared, right? Because this, we need to get we've got to get I2 back, all right? If you go back to the diagram, we've already figured out what this current is. So now we have to figure out what that current is, right? We're doing it without knowing this, okay? So we know what the answers are, but we're, we're trying to get if the current reference coming through the 10 ohm resistance is the reference direction is downward, we know the answer is 5 amps. Okay, so we're not there yet. All right. So what we're going to do though is go back up to this reduction where we had this equivalent there, right? Because we would have had the voltage here, V2, and let's keep the polarity the same there. All right. Again, this equivalent was based on these two in series, right? So what we need to find though is the voltage going through this equivalent, okay? It's not the same as 100 volts, right? Because these things are not in parallel, but by VDP, so I'll just put it over here, by VDP, we know how to do this by the voltage division, which occurs when you have two resistances in series. I know exactly what that voltage has to be, right? So V2 in this case has to be a fraction, all right? The fraction is the fraction of that resistance to the total, right? So the total resistance is 10 ohms, okay? And that would be multiplied by the 100 volts. But the REQ is just 5, so it's half. So that's not too surprising. The 100 volts is being applied through two resistances of the same ohmage. So therefore, the voltage must be split evenly. So that's not surprising. 50 volts there, 50 volts there, okay? Because the proportions are the same. That's VDP. It's only because the proportions are the same, half and half, okay? All right, so therefore, that's given us the voltage through that equivalent. Well, the voltage through that equivalent would have to be the voltage through the same as the voltage through the RE. Well, I guess it'd be the REQ1. I didn't write that up there. REQ1 equivalent, right? Because those were in parallel there, right? And so having done that, and when I know the resistance and if I know the voltage, I must know what the current is, all right? So therefore, I2 in this case would have to be simply, again, Ohm's law, be V2 divided by the 10 ohm resistance, okay? Right? Because, again, this is the analysis we did, but let me make sure this is clear. In representing this voltage here, okay, this voltage is represented for an equivalent resistance of 5 ohms. But what is that equivalent? It's an equivalent of these two things in parallel. So whatever V2 is here, that's exactly what it is there, plus and minus, okay? Again, if that equivalent is associated with two parallel resistances, then that is the same voltage through both of them, okay? Therefore, I have the voltage through the 10 ohm resistance, and I'm dividing it by 10 ohms. And of course, this is going to be 50 volts divided by 10 ohms. And there we have it, 5 amps, which is the correct answer, according to what we did with mesh currents, right? Again, this is just what we've done before. Again, the only tricky part, again, is when you roll back, you got to make sure you're looking for, like this case, we knew that if we could get the voltage through the 10 ohm resistance of the original circuit, then I know what the current has to be, all right? But to get it, I have to use the fact that I know that the voltage through this equivalent must be the same as the voltage of those two, because this equivalent represents two things in parallel. If they're in parallel, they're sharing voltage, okay? If they're in series, they're sharing current, okay? That's the difference, right? So one more instance is just, again, just as a practice, it's a good review. We'll do the same problem one more time, but this time we will use Kcl equations, okay? Just so that we can see that we use NVA as well as equivalent resistances. So we're actually solving the same circuit problem 3 different ways, okay? So in this case, we're going to do Kcl nodes, and notice that because we're doing NVA, we have a reference node down here, we've taken it down here at the bottom. So voltage polarities for these nodes, plus top of the arrow, negative at the bottom. Same thing towards this direction from the reference node up to the nodal voltage, okay? So we're again using nodal voltages. Let's do KCl. It's a good review. We'll do KCl node 1, and we'll do KCl node 2. So we're writing current equations, okay? All right. And again, our goal is still to get the current, and we'll make sure the reference direction is, we're still trying to go downward through that 10 ohm resistance, right? But we're going to represent for node, again, we're going to represent, let's say, outgoing currents for node 1. So if we go from node 1 to the ground, you're going to have V1 minus 0 over 10. So we'll have V1 over 10. If you go from the left, so V1 to the 100 volt resistance, 100 volt source there, you're going to get what? Plus V1 minus 100 over 5. And then you go to the right, and you would have plus V1 minus V2 divided by the 7 ohm resistance, and that has to be equal to 0. Okay. What about node 2 over here? Again, start from the node, go to the ground. That means you would have V2 over 3, or V2 minus 0 over 3, which is the same. Plus what? Just one other case. V2 goes to V1, so plus V2 minus V1 over the 7 ohm resistance, and that has to be equal to 0. Okay. Again, maybe by doing substitution very quickly here, let's clean up this bottom equation. If we multiplied through by 21, so in other words, we could say, well, if this sum is equal to 0, then 21 times it has to be equal to 0. So I'm just going to do this on the side over here so we can see how that cleans up for us. Well, that would mean 7 times V2 plus 3 times the difference V2 minus V1 would have to be 0. And then cleaning that up a little bit, you've got collecting your voltages here. We'd have what? We could write it as minus 3V1 plus 10V2 has to be 0. Or you could solve for V2 and show that V2 is 3/10 times V1. So we have that relationship between the two nodal voltages. And then what we would do is substitute 3V1 over 10 for V2, let's say, into the Kcl node 1 equation. And we will do that below, okay? So if we do that, what will we have? Coming up here, you'll have V1 over 10, right? Plus V1 minus 100 over 5, plus the quantity V1 minus, and here we go, 3/10 V1 all over 7, and that has to be equal to 0, okay? And with some collection of terms here, you can see what the coefficients are going to be on the V1. You're going to have 1/10 plus 1/5 plus 1/7 minus 3/10, all of that times V1, correct, is going to be equal to what? Well, you're going to have 5 over, negative 100 over 5 is going to give you negative 20. Pull it to the other side, it'll be a positive 20. Then you would just get a common denominator for all this stuff. And when you do that, it should collapse down to 28 over 70 times V1 equals 20. And then you can show, just using a calculator, it doesn't take you long to show that, in fact, V1 is just 50 volts. Okay. Right? So what we found is that the nodal voltage V1 is 50 volts, okay? That's the voltage through the 10 ohm resistance. Therefore, by Ohm's law, current through the 10 ohm resistance is I is equal to, you're going to have the voltage divided by the resistance, which is 10 ohms, and get 5 amps, okay? Again, the same answer, we already knew that, okay? So that was just to verify the original problem with mesh currents twice using our other methods, but it shows you that for the same circuit, there are a variety of different ways. Even though we talked about mesh currents being useful for very complicated circuits, they can also be used for simpler ones, okay? So if I'm asking you on a quiz, for example, to use mesh currents, or I could say it doesn't matter which method, then you have the option of using mesh currents. Sometimes, just to make sure you demonstrate that you can use a variety of methods, I may ask a specific method that I'd like you to use. But you can see the beauty of mesh currents in terms of, this kind of calculation can get you into trouble because of all the fractions. But if we return back to what we had to do for mesh currents, actually it was pretty simple. It was not, the substitution was not that complicated, and it was very easy to determine what that current was. So we will continue on in this very brief chapter by looking at more complicated use of mesh currents when you have other current sources, independent current sources in the circuit and how does that affect your use of mesh currents to resolve the unknowns that are sought, okay? All right, so that's enough for today.